Okay, guys, now we are doing lecture 6. It's about suffocate perfect Nash equilibrium. So far, we've learned about um, the basic structure of an extensive form game. However, we haven't learned about how to find an equilibrium or a prediction. When we were talking about a normal form game, we used the concept of Nash equilibrium or IESDS to find an equilibrium in a normal form game. However, because we haven't learned anything about uh, solution concept of this dynamic game or extensive form game, the first option that we can do is to use the same solution concept of Nash equilibrium. Okay, so in order to do that, if possible, we should um, change the form of a tree to a normal form game. By doing so, we try to apply a normal form of Nash equilibrium in a normal form game. So let's check whether this kind of an extensive form game can be transformed to a normal form game. First, let's look at this game. Here are two players, first player and second player. Okay, once the game is started, the first player will choose between L or R. If the first player chooses to left, then the second player will choose between L prime or R prime. Depending on the second player's action, they will receive their payout. The first one is the first player's payout, the second one is the second player's payout. If the first player chooses to right, then the second player uh, has a chance to choose between L double prime or R double prime. By doing so, they will get their payouts. So that's easy part. Now, remind the normal form game. Normal form game, gamma, for example, consists of, this is an extensive form game, but we will check whether we can transform this kind of game to a normal form game. Normal form game, first element was player, right? And the second is a strategy, right? And the payer. And they don't care about orders, or they eliminate the information about orders. Here in this game, first player will play the game first, then the second player, after observing the first player's action, then the second player will choose his or her action depending on the situations. So here are orders. Here is the order. But in a normal form game, we are squeezing orders so that it's like they are playing a game simultaneously. That's the only difference between this normal form game and extensive form game. And now look at this. So to construct a normal form game, we need three components: player, strategy, and payer. We can exploit this information from this game tree. So if we look at this game tree, we know that player is just first player and second player. Now think about the strategy. Well, the first player strategy is very simple because the first player faces just one kind of contingency. I mean, a situation that the first player will face is just at it will be happening in at the initial node. So so the first player strategy is L or R. This is the first player's strategy set. Now think about the second player. Actually, second player will face two different contingencies. First contingency occurs when the first player will choose L. Then this node will be reached. Then second player will face the time when the second player can choose. And this is another contingency. I mean, if the first player will play all, then this node will be reached. Then the second player will have a time when she or he can choose his or her action between L double prime or R double prime. So think about that. In the first contingency or in the first node, then the second player will choose between L prime or R prime, right? And then times in the second contingency, he or she will choose between L double prime or R double prime. If I expand everything about that, actually it can be expanded like that. I mean, picking one element here and other element here, we can generate every possible combinations of strategies like that. L prime, R double prime, and R prime, L double prime, R prime, or R double prime. So this is the second player's strategies, okay? And depending on that situation, they will get a pair. For example, if the first player is choosing all as a strategy, and the second player is choosing this as a strategy, then look at this. If the game is started, the first player will choose all. I didn't talk about the reason why the first player should choose all. I just arbitrarily picked up all and L prime and R prime. And the second player will choose L prime here if this node is reached. And if this node is reached, then the second player will choose R double prime. So that is the strategy. And once the game is started, because this player will choose all, and the game is passing this path, and at this node, because the second player will play all the prime, this game is choosing this path. So at the end of the day, they will receive these payouts. Okay. Likewise, depending on this kind of all possibilities, we can generate kind of payouts. Okay, that is payout. So reminding the basic form of normal form game, we need a player strategy, and also we can generate payout. This is P. Payouts. So basically that is a way of generating a basic, a normal form game. So let's do that. Okay, as you can see, we have two Nash equilibriums. One is that L and R prime and R double prime, and player was playing R, and second player is playing R prime L double prime. So there are two Nash equilibrium. Now, if I'm representing this Nash equilibrium and this Nash equilibrium, then look at this. This is the first player is playing L, okay, and the second player is R and R double prime. Then they will get this equilibrium, this outcome. That is the first Nash equilibrium. Or regarding this, first player is playing R, and the second player is playing Al prime and L prime. So they will get this as an outcome. That is another Nash equilibrium. That is the basic way to find a prediction or equilibrium. Okay, let's continue with another one. I think this would be more familiar for you. Look at this game. This game is a little bit different from the previous game. One is that here is a dot line, okay, which means at this node, player has the same information level. I mean, previously, when you're playing this kind of game, the player here and the player here has different information. For example, the information that this player has at this node is that, for example, the first player played L. That is the information. At this node, the second player has different information such that the first player played R. So that information levels are different at this node. However, by connecting these two nodes, we now know that the information level here and here are the same, in a way that the information level here and here is like first player played one action between L and R, but we don't know, he or she doesn't know which exact action is played. Okay, that is information that player has at each node, so that player cannot distinguish where he or she is standing. Okay, also as we can see, the name of the action that player can choose at these nodes are the same. Just L prime, L prime, L prime, and L prime. But because the branches are the same, I mean, the second player cannot aware of where she or he is standing depending on the actions that the second player can choose at each node. Okay? But the outcomes can be different. I mean, which means when she is taking this action or this action, even though she cannot distinguish which action she can take, but the outcomes can be different. Also, it also means that second player cannot know what kind of outcome will be happened by choosing these strategies or actions at this node. Okay, anyway. Okay, let's continue. As we can see, the information levels at these nodes are the same for the second player. So that the second player cannot distinguish between L and R. Okay, what the second player knows that just the first player played an action before, but I mean, which action the first player choose, she or he cannot know that. That is exactly the situation usually we can describe with this kind of normal form game. Let's exploit the information here. First player. Player set is first and second player. And action, the first player will choose L and R. Right? Now think about the second player's strategy. Here, second player has just the same information, even though, I mean, exact node the second player is standing is different because she or he cannot know that, so that for the second player, I mean, the place, the node the second player is standing is the same place. So it just refers to just one contingency, not the two contingency, so that the strategy set for the second player is just L prime and R prime. right? Think about that. For example, in this situation, if the first player is choosing R and the second player choosing L prime, think about that. What it means, first player is choosing R and second player is choosing L prime because she does not know where she is standing. So once these things is happened, no matter what, the second player will choose L prime. Okay? So in this case, the outcome they will get is 2, 1. Okay? So based on this, we can construct normal form game. But interesting here is that, by the way, before saying like that, at this node represent the information set. This is an information set. This is the same information set because the information level is the same. But without this dot line, this information set is different from this information set. But here, those are in the same information set. Anyway, well, I mean, when I try to transform this kind of game to a normal form game, you know, usually I said that orders is eliminated from a normal form game, right? Or if I'm saying the same story in an information level, I mean, here from here to here, some kind of information is lost. However, here and here, actually, there is no loss of information because the second player, when she is, I'm just, the second player is she, okay? So the second player, when second player is trying to choose an action, what she's knowing is that just the fact that the first player played before, but what action doesn't know what action the first player played, right? I mean, in terms of timing, it's like there are difference between the first player and the second player. There are difference of timing. However, for this kind of normal form game, simultaneously means technically it may mean they are playing their game, their action at the same time, but also when they are choosing, it means when they are choosing, they don't know what kind of action other player is playing. This is exactly the same situation that this extensive form game is describing. So from here to here, actually there is no loss of information, right? What it means, in some cases, we can describe this normal form game as an extensive form game without loss of any information, right? So what we can see here is that actually this game and this game are equivalent. Can you see that? Because this is extensive form game can be changed to this normal form game without loss of information. There's no loss. Okay? And with this 3 component, this game is played with this, can be illustrated by this extensive form game. As we can see, it's very useful and very exact. So there is nothing happened here. Also, there's no loss of information, so that these two games are equivalent. The same game, okay? But going back to the previous slide, this one, this one and this game is not the same. This can be represented by this kind of game, for example. However, when we try to represent this game, this extensive form game, to a normal form game, we actually remove information orders. We got rid of order information, right? So that this game is not exactly representing this game, because in this game order information is not reflected. But here, there is an order. But again, in this game, from here to here, there's no loss of information. So these two games are the same. What it means, the normal form game is a subset of extensive form game. Okay, some game can realize some normal form game. Normal form game can be realized as an extensive form game, but there are some extensive form game cannot be realized as a normal form game. So actually, this normal form game is a subset of extensive form game. Okay, that's one thing you need to understand. So anyway, let's solve this game with using on Nash equilibrium. If the second player is playing L prime, I'm going to choose L and L in this case, so that this is a dominating strategy for the first player actually. And when the first player is playing L, the second player will choose R prime. So this is only one Nash equilibrium. L and R double R prime. So that we get 1, 2. This is the Nash equilibrium. Okay, so now I explain the first way to find an equilibrium of this extensive form game. The first way is to transform this extensive form game to a normal form game, and in a normal form game we try to find a Nash equilibrium. What it means, as I already explained, there are two types of in equilibrium. One is that a pure strategy Nash equilibrium, and the other one is the mixed strategy. Mixed strategy Nash equilibrium, right? But usually we are focusing on just the pure strategy Nash equilibrium. If we are considering a mixed strategy Nash equilibrium, it would be more a little bit more complicated. But anyway, so now at this time we are focusing on pure strategy Nash equilibrium. Okay. Okay, so let's continue one more exercise. This one. So this is a game called an investment game. I mean, this is not a game I created. The other researchers created. This is very interesting game. So here are two players, player 1 and player 2. Usually, player 1 refers to a wife and player 2 is her husband. Maybe you can exchange it, vice versa. So anyway, the first player, I mean the husband, this is a husband. Husband wants to run his own business. It's like he's working at his workplace, but he now wants to run his own business. Okay. First player can support her husband, or maybe does not support her husband. Okay. If the wife does not support her husband, they will get a certain pay up. It's like this is a status quo pay up, or just a normal pay up. Okay. Now, if her wife support the husband, say that husband will succeed in his business. Problem happens, the next time. Maybe, this husband, after succeeding, can return to wife and live peacefully and very thankfully. But after winning his business, maybe he can find another partner, maybe betray the wife. Okay. If the second play, the husband is returning to his wife, because the husband won his own business, their payups are both increasing from 1 1 to 2 2. Okay? But now think about another case. After the husband succeed, he is thinking about all the thinking. He's trying to betraying his wife and try to find another partner, like a divorce or maybe some other woman, something like that. So just try to, I mean, try to find a partner. As a result, husband will be better off a lot, enjoying every increased happiness, but wife get worse because he used her money to his wife, and then her wife betrays, I mean, the wife. So the wife's payoff is decreasing from 1 to 0. Okay, this is a kind of trust game. Another name of this investment game is called trust game. Okay, so another name actually of this investment game is trust game. So in that case, they will get those kind of outcomes like that. Okay. Now let's analyze this game. The only tool we can analyze this game is to find the Nash equilibrium in a normal form game form. So let's find the first players. Player set is wife and husband. Wife is player, first player, and husband is the second player. Now think about the first player, wife's contingency. She has just only one contingency or one moment that she can choose, right, at the initial load. What she can choose is supporting or not supporting. So support, or not support. Now think about the second player, husband. Well, in this case, this is a terminal load. There's nothing that the second player, husband, can do. Only when this node is reached, then the second player, husband, can do something, right? Once that contingency is reached, then the husband can choose between another partner or return to wife. Okay, again, these are terminal nodes. There's nothing that the husband can do. At this node, there's nothing that the husband can do. So only contingency that the husband can face is when this node is reached by wife's support. Okay, so based on this, we can construct this normal form game. Look at this. Wife and husband. This is a strategy of wife, this is a strategy of husband. If wife choose support and return to wife, then wife choose support, and the second player, husband, return to wife, then they will get 2, 2. If wife choose not to support, in what kind of strategy the husband is choosing, well, they will get 1, 1, right? And wife support and the husband is to find a new partner, then they will get this payout. Okay, this is a kind of realistic example, and I'm letting you know how to make a model based on game theory. Then now look at this. In this form, we can solve this just by using a Nash equilibrium. From wife's perspective, if husband is choosing out to wife, then she's better to support. But husband is choosing to find a new partner, it's better not to support, right? Then wife is choosing support, then husband will choose find a new partner, but it's not support. I mean, it's indifferent between choosing these two strategies. In that case, only one Nash equilibrium is this. Wife does not support, and husband will choose find a partner. Okay? I mean, I'm not arguing that this is just what in real is happened all the time. Someone may choose this kind of path, but some may not choose this kind of path. But as long as we are setting up the outcome in this sense, and if we assume that players are selfish and rational, then this is one kind of future, one equilibrium that this game or this game form is talking about. Again, however, in practice, a wife may support her husband's business and her husband is not betraying because of guilt, or her husband may not betray his wife even though he succeeds. Okay, I mean, in order to analyze that kind of situation, we need to just beyond what we have been doing based on selfishness and rationality. We need more, like guilt or maybe social norms that is not implemented here in this game theory. I mean, I'm not saying that there is no game theory which deals with that kind of thing. There are game theory which deal with that kind of thing. That is also called psychological game theory. Psychological game theory. Those kind of game theory deal with emotions, social norms, or people's expectation, and so on and so on. However, that's too complicated, so I'm not going to talk about that here in this class. Okay. Okay, as I said, I mean, I just explained the first way to find an equilibrium in an extensive form game. That is, first transform an extensive form game to a normal form game. When we are doing that, we are losing some information. But anyway, once we can transform an extensive form game to a normal form game, we can find a Nash equilibrium, right? We can use a Nash equilibrium concept. Seems to be okay, right? But going back, but one thing, there's one thing we need to think about. That is that we didn't use some information of orders. I mean, when we are illustrating, when we are describing a game in an extensive form game, it means there is some kind of information about orders. But if we just try to find a Nash equilibrium, we are not using that information. From the beginning, we do not try to use that information, order information from the beginning. We don't need to make an extensive form game. We're just using a normal form game. That was enough, right? It doesn't make sense, right? If we try to use order information, if we don't try to use order information from the beginning, we don't need to draw a game tree. Just to use a normal form game, that's enough. However, I mean, when we are making a tree, an extensive form game, it implies that we try to use order information. But when we are using a Nash equilibrium concept, we cannot use that. Sometimes it's a problematic. Let's look at that example. How about this? I already explained this game, so this game, this extensive form game, can be transformed to this type of normal form game when we know that there are two Nash equilibrium. Let's look at this equilibrium. This Nash equilibrium is that first player is playing L and second player is playing R and R double prime, R prime and R double prime. Right? I'm going to describe that one here. First player is playing L and second player is playing R and R double prime. And this is the outcome they will get. Seems to be okay, right? Because this is a Nash equilibrium. However, think about this point. Okay, I mean, in this case, the reason why the first player does not have any willingness to deviate from current Nash equilibrium is because even though the first player is changing to R, I mean, what the first player can get is 0. 0 is less than 1, so that first player doesn't have any incentive to deviate, right? Here, first player doesn't have any incentive to deviate from this Nash equilibrium because the first player deviates, what the first player can get is 0, right? So it doesn't have any reason. However, that's Nash equilibrium's rationale. However, let's say that even though the second player can play this combination of a strategy, R prime and R double prime, well, because of some kind of error, like the first player just tried to, when the first player just tried to push the button between left and R, just because of some reason, maybe the first player is very old, or so that his hand is trembling. So by chance, I mean, even though the first player knows that the second player will play this strategy, and first player has willingness to play R, but by chance, first player just chose R. It happens just by chance. Okay? So, I mean, second player at first just try to play R prime and R double prime, likewise, and the first player by chance choose to R. So this node is reached. Now, second player is standing here. Now we'll think, okay, at first, before the game is started or ex ante, second player has a strategy to play R prime and R double prime. Now, once the game is reached at this point, second player will compare the payoff that second player can get. Because the past cannot reverse, it just happened, and the second player has nothing to do change it. Even though the second player has a plan to play R prime and R double prime before the game is started, but by chance, if this node is reached, actually to play R following her first plan to play R double prime is ridiculous, because if she is playing R prime, what she can get is 0. 0 is less than 1. That's worse. So even it's reasonable to say that even though second player has a plan of playing R prime and R double prime before the game is started, but by chance, if this node is reached, then she will play L. it's more reasonable for the second player because 1 is greater than 0, right? In some sense, this Nash equilibrium is not credible. It's not credible. Why? Why this is happening? Because, we find a Nash equilibrium here. However, we didn't use the information about orders. When the second player tried to play his or her action, she has an information that the first player already played all, right? The second player didn't use that information. Here, the reason why the second player can choose L prime and double prime if the first player is playing L, right? Even though second player is changing L prime to L prime, the payups are the same. So the second player doesn't have any reason, right? Right? However, here, if this is really happening, when they are choosing this kind of strategy, they made a strategy here before the game is started. But once the game is really started and if they reach this node, then the second player surely will choose L prime. So it doesn't make sense, right? Because when we are looking for Nash equilibrium, we didn't use that information. That's critical. So that this Nash equilibrium is not credible. Let's think about this equilibrium. R prime, R prime, L prime. Okay, even though this node by chance is reached, then 2 is better than 1, so that second player will choose R prime. So at this node, second player is choosing L prime. In that sense, first player doesn't have any incentive to deviate from playing R, even though changing to L, what the first player can get is 1. So that first player will stick to playing R, and second player will play R prime and L prime, L double prime. That's okay. So in some senses, this is credible Nash equilibrium, but this is not credible Nash equilibrium. We need to distinguish that. So another concept is created, that is subgame perfect Nash equilibrium. Subgame perfect Nash equilibrium. A Nash equilibrium, among Nash equilibrium, some Nash equilibrium will be subgame perfect Nash equilibrium. If the player's strategy constitutes a Nash equilibrium in every subgame, what is subgame? Going back to this game, the reason why this is not an equilibrium is because once this node is reached, in this small tree, this isolated small tree, the reasonable strategy that the second player can choose is not the same as this Nash equilibrium. What it means, in order for strategy to be credible, even in small game, the game should be reasonable, or we find a Nash equilibrium from before the game, right? But it's reasonable to think about if this node is reached in this small tree. Also, we need to check whether players are playing a reasonable strategy, or in other words, we need to check the strategy is a Nash equilibrium even in this small game, or even in this small game, or even in this from the original game. We need to check whether strategy is a Nash equilibrium. In that criteria, we can narrow down more credible strategies. Look at this. Again, there are two strategies of Nash equilibria. But here, in this small game, let's say that once this node is reached, we don't need to care about the others because there's nothing that we can change. So that just focus on this small tree. Then the second player surely will choose R prime, right? So at at the first information set here, first player should play R prime all the time, R prime at the first node. So it doesn't make sense at all from the beginning. And in this small subgame, second player will choose L prime, L double prime. It doesn't make sense at all. Only remaining strategy that the second player will choose is R prime and L double prime here. And then from the first player's perspective, if the first player is choosing L, second player surely will choose L, so the first player will get 1. If the first player is playing L, surely the second player will choose L prime, so that first player will get 2. So that first player surely will choose L. So that this is only, credible Nash equilibrium. This type of credible Nash equilibrium is called subgame perfect Nash equilibrium. Okay, and this is small game. This is small game. This is small game is called subgame. This is also subgame. This is also subgame at the same time the original game. But now look at this. Well, this is the original game or subgame as well. But this is not the subgame. Even though second player can try to play a game, she is not knowing where she's standing because of this dot line. Because these two nodes are in the same information set. So, nodes in the same information set cannot be isolated or cannot be spread out. Okay, so this is not one subgame. It should be in the same subgame, so that here in this game there is only one subgame. Okay, so that when we looked for Nash equilibrium here, Nash equilibrium was, I think, this. So this one, L and R prime is only one Nash equilibrium and credible Nash equilibrium. Can you follow the meaning here? Because, second player cannot know where she is standing. So, it cannot be generate a situation that second player by chance can choose somewhere. It doesn't matter. Even though the first player is choosing R prime again by chance, because she doesn't know where she's standing, still she's going to choose R prime and R prime at all. Okay? So that is this is one, it has just only one subgame, but this game has 3 subgames, this one and this one, this one. How about this? Okay? Well, once this node is reached, then the second player will choose between those two, and then the second player will choose this one. Right? Once this node is reached, all the others cannot be changed because that is past, or the past already it's given up. Okay, so it has 2 subgames. this game, because this is another information set. This is a independent information set. This is also independent information set. So here are two subgames. Okay, so we already find the Nash equilibrium not supported and find the partner. So this is a Nash equilibrium, and this is also subgame perfect Nash equilibrium. Why? Because when the game is shrink to this subgame, because the wipe is choosing not support, then this node cannot be reached. But by chance, maybe the wipe get to that node, then surely husband will find another partner because 4 is greater than 2. So this is not violating rationality once this game is played. So this is a Nash equilibrium. At the same time, this is a subgame perfect Nash equilibrium. We just use SPE. Again, but some Nash equilibrium is not a subgame perfect Nash equilibrium. What it means, actually, subgame perfect Nash equilibrium is a subset of Nash equilibrium. So you may remember this. IESDS includes a superset of Nash equilibrium. Include your Nash equilibrium and SPE. Then Nash equilibrium is a subset of IESDS because some IESDS the strategic profile is a Nash equilibrium. In the same sense, SPE is a subset of Nash equilibrium. Sub-Nash equilibrium is not an SPE. Between those two, because SPE is using information about orders, this is a more credible information than the Nash equilibrium. Okay? So we need to find the subgame. Subgame begins at decision node that is a singleton information, includes all decisions and terminal nodes following in the game tree, does not cut any information set. It means nodes are, if nodes are in the same information set, it cannot be cut. Okay. Before playing this one, let's look at this one. How many subgames do we have here? It will be your quiz for you, but look at this. Original one is the subgame all the time, and once this node is reached, and this game will be played. So this is another subgame, because the player cannot distinguish between these two nodes. This cannot be cut. But here, once this node is played, then this will be played on the subgame. So here there are 3 subgames. 1, 2, 3. Okay. The other one is for your quiz. How about this? Another one. How many subgames do we have here? Well, these nodes can be played independently. Seems to be, right? However, player cannot distinguish the 3, so actually, here is 1, and this cannot be cut from the beginning, right? So it's like there are just 2 subgames, because those 2 nodes cannot be cut because these 3 nodes are connected, so they are in the same subgame, but just for this node. If the first player is playing R, second player is R prime, then who is the player who's playing this game? It should be 3, I think. Anyway, the third player will know where the third player is standing, so this is an isolated subgame. All the others is in the same subgame, so there are just 2 subgames. Okay, So anyway, that will be for your quiz. So I'm stopping here. It will be very helpful to understand. It will take time to understand subgame perfect Nash equilibrium, but try to do that. Well, your quiz is this. Try to do this. I mean, here is a game called Ultimate Game. There are two players, a proposer and recipient. They are negotiating of dividing $10. First, the proposer suggests giving X dollar per the recipient. Maybe the recipient can take it, that offer, and they will divide that 10 bucks. 10 minus X dollars for the proposer. X is for the recipient. Maybe the recipient can reject that offer, then they get $0. So describe that game with the game tree and find all subgame from the game and find how many numbers of subgame exist in that tree. Okay, so we'll see. Okay, I'm stopping here.